Let's start recording this. Okay, so we're going to look at radicals, radical expressions, roots, in other words. So roots and exponents. There's a connection between roots and exponents. When you have, say, the cube root of x squared, another way of writing that is x to the 2/3 exponent. So what we see is the top number is the power, and the bottom number is the root you're working with. So this is the third root of x squared. So this gives us fractional exponents we can work. So all those rules that we talked about, rules of exponents, they still apply here. It's just you're going to deal with fractions for the first part of this section. The general rule here is RXP, x to the p divided by r. If there is no power listed, you're supposed to say, oh, I know, the power is 1, right? So this would be x to the 1 over r power. If there's no root listed, then that means the root number is 2. It's a square root. So if you don't have a number up here, it's a 2. We don't usually write the 2, but that's the understood. This is kind of the default one. So x to the 1/2, or 3/2, or whatever it is, power inside. If you're starting with, like, say, a cube root, and by the end of the problem you don't have a root number anymore, you're telling the reader that you are working with square roots. So make sure, if there's not a number there, that you are talking about square roots and not like cube roots or something else. So the first part of the assignment is just going to be things you've already done. It's going to be things like 4x to the 2nd, y to the -3, but now it's going to say something like to the 2/5 power. And you're going to say, well, okay, the rule of exponents is when you have a power to a power, you multiply those. So this is going to be 4 to the 2/5 power, x to the, well, this is 2 over 1, so top times top, bottom times bottom, just like you normally would multiply fractions. 3 over 1, so -6/5. And then, again, we don't like negative exponents, so 4 to the 2/5, x to the 4/5, y to the 6/5 on the bottom. So this is just going to be basically used, I mean, it'll get more complicated, but it's basically using those rules of exponents that we've done before, now with fractions. Or, say something like x to the 2/3 times x to the 5/3 minus 6x to the 9th or something, I don't know. So what are you going to do? You're going to distribute this, and then you're going to remember your rules of exponents. Say when you multiply same base, you add the powers. So x to the 2/3 plus 5/3 minus 6. You don't take this 2/3 times the 6. That's an exponent. It combines x to the 2/3 plus 9. So 2/3 and 5/3 make 7/3. minus 6. 2/3 plus 9 is 9 2/3, which, if you remember how to turn a mixed number into an improper fraction, 9 times 3, 27 plus 2, 29/3. And there it is. Now, technically, I guess that's in the wrong order. You know, if you wanted to write it in the right order, you know, higher power comes first. 29/3 is higher than 7/3. But, you know, that's this basic idea. So that second section, the first part, is just using those rules of exponents to deal with fraction exponents. You don't even need to know that these are really roots, except occasionally, like this 4 2/5, that's the 5th root of 16, 4 squared, right? Except you can't break down, you know, maybe I might want to write it that way, but I can't break it down, you know, because it's not a perfect 5th. On the other hand, if I had something like simplify, and I had 9x to the 4th, all of that to the 1/2, so 9 to the 1/2, x to the 4 over 1, again, power 2 power, multiply 4 over 2. Well, this is the same as the square root of 9. So what number do I square and get 9? 3. And then 4 divided by 2 is 2. So 3x squared. So this is the only place where it's really that it comes into an issue in this first part about, oh, those fractions are roots, is when you're dealing with a number, and that number can actually be broken down using the root. If it can't be broken down like this one could not be broken down. You could just leave it. And when you're dealing with variables, you don't even need to know you're dealing with roots. You just use your normal exponential properties. Now, the second part of this second section, they're going to ask you to simplify some roots. So let's talk about some common roots here. We'll start with variable. Well, I guess I'll start with numbers. If you know your perfect squares, then you know your perfect square roots. For example, I know 5 squared is 25. Oops, 5 squared is 25. So I also know the square root of 25, or in other words, what am I squaring to get 25, is 5. So squares and square roots are just opposite operations. It's just whether I'm going this direction, I'm going that direction. If I have a root, I'm going backwards. If I have a power, I'm going forwards. They're related to each other. Same thing with our perfect cubes. If you know 3 to the 3rd is 27, then you also know the cube root of 27 is 3. So you can break down anything that's a perfect cube or a perfect square. We should know most of those by heart by now, hopefully. Then you get things that maybe you got to think about a little bit. Say the 4th root of 16. Well, if you think about what times what is 16, you can think 4 and 4. Well, 4 is 2 and 2 and 2 and 2. So you got 2 to the 4th power. So what do you multiply by itself 4 times? That's what this is asking you. Gives you 16. The answer is 2. So it comes out to be a nice perfect 2. Let's say you're asking yourself, what times what gives you 16, and you didn't think 4 and 4. Instead, you thought 2 and 8. Okay. Well, 2's prime, so it's not going to go any smaller, but 2 and 4 makes 8. Well, again, 2's prime, and 2 and 2. So again, I'm back to having 4 2's. So that's a way you can break down bigger numbers to see, you know, what do I have? Always go down to the prime numbers. You can break those down. That's the hard stuff. The easy stuff is the letters. So the square root of x squared is x. The cube root of x cubed is x. The fourth root of x to the fourth is x. The fifth root of x to the fifth is x. So you can see anytime the power and the root match each other, you just get the letter. The power and the root cancel each other out. Now, what if you have the square root of x to the fourth? Well, that's x squared. What if you have the cube root of x to the sixth? Well, that's x squared. What if you have the fourth root of x to the eighth? Well, that's x squared. What if you have the fifth root of x to the 10th? That's x squared. So what we're seeing here, what's happening, remember, another way of writing this is 4 divided by, since this is a square root, 2. What you're doing is dividing the power by the root. 6 divided by 3 is 2. 8 divided by 4 is 2. 10 divided by 5 is 2. So if you had, what's the third root of x to the 18th power? You're going to take 18 and divide it by 3 and get x to the 6th. So all you have to do is divide the exponent by the power. So if I gave you, tell me what the cube root of 125 x to the 6th y to the 12th is, you would say, well, the cube root of 125, well, what times itself gives me 125? Well, ends in a 5, so probably 5. 5 times 5 is 25, times 5 is 125, so 5. And then 6 divided by 3 is 2. 12 divided by 3 is 4. That's the answer. So these are actually the easy ones. The letters are the easy ones. It's these numbers, you have to know those perfect things. Now, this isn't for this section, but it's going to help you for the next section. And I'm just going to touch on it here, and then we'll talk about it more in about 20 minutes or so. But let's say I want to, let's briefly mention non-perfect roots. What about that case? What if I have the cube root of x to the 7th? Well, I know I can divide 3 into 7, but not evenly. So what I'd want to do is I'd want to think of x to the 7th as x to the 6th, a number that 3 does go into evenly, and the biggest one that's less than 7, times an extra x. And then, sorry, 6 divided by 3 is 2. Now this part is just a leftover. It stays underneath the root. So what's gonna happen is when you have something that's not a perfect root, part of it's gonna divide in. You're gonna say, how many times does 3 go into 7? Twice with 1 left over. All right, give me a second. Okay, sorry. So part of this, you're going to say, how many times does 3 go into 7? Twice with 1 left over. That's what you're going to say. And that's how it's going to break down. It's really, if you think about fractions, exponents are fractions. So they're just fractions for powers. All right, so I'm going to give you about 20 minutes or so. Go ahead, even if you're not done with the literal equations, jump to the second section, 7.1. and try some of those problems. And again, if you have questions, let me know. I'll be happy to go over them. And then we'll talk about the last section. I want to try to leave as much time as I can for the last section because there is a lot in it, and I want to try to get through it all today. Okay. Excuse me. All right, so in this third section, we're going to look at using radicals and doing operations, adding them, subtracting them, multiplying them, dividing them. In order to add or subtract, a couple of things have to be true. First thing that has to be true is you have to be talking about the same exact root number. So if you try to add, let's say, a cube root to a square root, it's not going to work. Can't do it. So that's one thing. And then kind of an extension of that, even if the root numbers are the same, the part inside the root has to be the same. So if you had, let's say, 5 square root of 2x plus 4 square root of 3x, even though both are square roots, you can't add those together. They're not like terms. So for like terms, not only do you have to have the same variable, but you have to have the same root part. So something like 3x square root of 2y plus 7x square root of 2y. This whole variable and root part all match. So when you add them, you just add the number part in front, the coefficient part. So this is 10, and then the part that matches. Now, kind of a reminder, when you first learn about adding like terms, you know, I know, like I do for sometimes, is I kind of skip over the actual mathematical mechanics of this. And maybe if we briefly talk about it, this will make sense. What you do is you actually factor out this matching part. So this becomes 3 plus 7, and then this matching part gets factored out. That's why it doesn't change. And it's just the other part, the non-matching part, that gets added together to make the 10. So you kind of think, you know, keep that in the back of your mind. I don't usually make a big deal about it, but if you're ever wondering why isn't this back part changing when I add or subtract, it's because you're really factoring that common part out and then combining the rest. Now, sometimes things don't look like they match, but they actually do. So for example, let's say we were to simplify the cube root of 24 x cubed y to the 5th plus the cube root of 81 x cubed y to the 5th minus 4xy cube root of 3 y squared. So right now, none of this matches. Some of these have maybe some variable part that kind of looks like it matches, but then the root part itself, the 24 and the 81, that doesn't match. This one doesn't match. You got x's and y's on the outside, you got y's on the inside. So as it's written, it doesn't match. But what we need to do is break each one of these down. This one's actually broken down as much as it's going to be broken down. So I'm just going to rewrite that one. But these other ones can break down. So what I'm going to do is I'm going to look at the numbers, and I'm going to ask myself, what times what is 24? And keep in mind, we're talking about, in this case, cubes. So subconsciously, you know, in the back of my mind, I need to keep having, you know, oh, 1 is a perfect cube, 8 is a perfect cube, 27 is a perfect cube, 64 is a perfect cube, 125 is a perfect cube. So I'm going to think about that stuff as I'm thinking about what times what makes 24. So looking at these, I should jump into my head that 3 times 8 is 24. Now, why do I want to, you know, sure, 2 times 12, 4 times 6. But because I'm talking about cubes and I know 8 is a perfect cube, I want to think of it this way, 3 times 8. 81 is 3 times 27. Again, 27 is a perfect cube. So I want to think of that instead of like 9 times 9. Or I guess that's pretty much it. 9 times 9 or 3 times 27 or 1 times 81. But I want to think about perfect cubes. What are the perfect cubes? So what's the cube root of 3? Well, the cube root of 3 is the cube root of 3. It doesn't break down. What's the cube root of 8? 2. 2 is what you cube to get 8. Right? This is 2 cubed. And then, again, with the letters, you just divide. So 3 goes into 3 once, so I get 1x. 3 goes into 5 once, so I get 1y with 2 left over. And then 3 times 27, again, the cube root of 3 is just 3. The cube root of 27 is 3, right? This is 3 cubed. Again, 3 goes into 3 once, so I get 1x. 3 goes into 5 once, so I get 1y with 2 left over. And now, xy cube root of 3y squared, xy cube root of 3y squared, xy cube root of 3y squared. So initially these did not look like they matched, but once I broke these down into what could break down and what couldn't, now they all match. So 2 plus 3 is 5, minus 4 is 1. So 1 xy cube root of 3y squared, that's my answer. So when you're adding and subtracting, you're looking for what breaks down, what doesn't break down, getting these to match. And if they can match, then you can combine the front parts. Now, sometimes even if you break them down, they still won't match. But that's not usually how these problems are set up. Usually these problems are set up so that they will match and you will be able to combine. All right. I'm going to pause there. I'm going to let you try some problems with the adding and subtracting. So go ahead and jump over to 7.2 again, even if you're not done with the first couple problems. Or first couple sections. I want you to try the beginning of 7.2, the adding and subtracting. Then I'm going to talk about the multiplying, and then we'll talk about dividing. So I'm going to give you about 10 minutes or so. Try adding and subtracting. Try some of those problems. And again, if you have questions, let me know, and I'll try to answer them. So look at multiplying. And then I'll give you a little bit of time to work on that, and then we'll look at dividing after that. And dividing is the really complicated one, but I'll talk about multiplying before you can talk about dividing. So multiplying roots. And you'll see me say radicals and roots interchangeably. That's pretty common. They're just different phrases for the same thing. So when you're multiplying roots, the outside times outside, and then separately inside times inside. So if you have 3x square root of 2y and you multiply that by 5x square root of 6y, then that's going to give you, you're going to multiply the outside parts together. And it doesn't, you know, even though I made these like both x and x, they don't have to match when you're multiplying. But these do, so 15x squared. And then the inside part we're going to multiply together. So 12y squared. Now that I multiply those, I need to break it down if I can. So looking at this root part, and again, I'm thinking square root, so I'm thinking squares. And again, squares 1, 4, 9, 16, you know. Well, 12 is 4 times 3. And, you know, I'm thinking 4 because of perfect square. So the square root of 4 is 2. The square root of 3, well, square root of 3 is the square root of 3. And then y squared, the square root of that, well, again, think of this as like an invisible 2 up here, right? 2 divided by 2 is 1. So 1y. And you just clean it up. 15 times 2 is 30. X squared y, x squared y. So remember, when you're multiplying, things don't have to match. They can be totally different to multiply. Except, in this case, the root number has to be the same. There are ways to get around that problem, but you shouldn't have to. They should always match in your case. Then, these can get a little bit more complicated. You might run into situations where you might need to ask yourself, do I want to simplify before I multiply? Let's say I have the cube root of 16 x to the 4th y squared times 2 cube root of let's see, 54 x cubed y. Do I want to try to break these things down before I multiply, or do I want to wait till after I multiply? And really, it's kind of what's most convenient for you personally. A lot of times, like with the letters, I don't worry about breaking them down ahead of time. I'll break them down afterwards. But with the numbers, since the numbers can get kind of big, I might want to break those down now. So like 16, I might think, okay, well, that's 8 and 2. 54, that's 27 and 2. So cube root of 8 is 2. And then with 2 left over, and then x4 y squared. Again, you could break down that x4 if you wanted to, but I usually don't, because the letter's going to break down again usually after you multiply, so I'm not going to waste my time with it. Cube root of 27 is 3 times the 2 that's already out there makes 6. And then this, again, left over 2 x cubed y. And then I'm just going to multiply outside parts together, inside parts together. So 12, that's a 2 and the 6. Cube root of 2 times 2 is 4. X to the 4th times x to the 3rd. Remember, when you're multiplying, add exponents. So 4 plus 3 is 7. Y squared, y makes 2 and 1 make 3 y's. Y to the 3rd. And now I can break down the letter parts. By the way, what's the cube root of 4? Well, 2 times 2. There's only 2 of them. It's not a perfect cube. So again, the cube root of 4 is still the cube root of 4. X to the, 7 divided by 3. Well, 3 goes into 7 twice with 1 left over, right? 6 and 1 extra. Got this 12 out here still. And then 3 goes into 3 once, so 1y. And evenly, so there's nothing left over. So there's your answer, 12x squared y cube root. And a lot of times I might just rewrite it, because when I'm kind of piecing it together like that, it's kind of spread out. It looks ugly, but you don't need to do that. This would be fine. This would be an okay answer. Now, when you're multiplying, you might also need to multiply binomial type of expressions. I mean, they're not binomials because these aren't polynomials, but you know what I'm talking about. 2-term expressions multiplied together. And so to do that, you're just going to do, the FOIL, right? You're going to repeated distribution. So you're going to take 5 times 7, 35. 5 times 4 root 3. Again, outside parts multiply together, inside parts multiply together. So 5 times 4 is 20, positive 20, and then times a root 3. And then the I part, inside parts, negative 2 times 7, negative 14, and then again times a root 3. Negative 2 root 3 times 4 root 3, so the negative 2 and the 4 multiply together, negative 8. Root 3 times root 3. Again, inside parts multiply together. That gives you 9. Remember, when you're adding, it doesn't change. But when you're multiplying, it does. So that changes. Now I need to pretty this up. And hey, square root of 9 is the number 3. So this is negative 8 times 3. That's negative 24. So that's going to combine with the other constant without a root. I mean, all these are constants, I guess. There's no variables. But the other non-root part, and that's going to give me 11. And then both of these have root 3. So 20 minus 14 is 6 root 3. And again, when you're adding or subtracting, the root part, the number part doesn't change in the root. It just matches. So foiling, if you throw x's in here, you just FOIL it like you normally do. But two binomials, basically, is what you're doing, multiplying that out. Okay, let me give you, again, about 10 minutes to work on this. About 10 till, we'll talk about dividing, and you can check that. Then the rest of the time, you can ask questions or whatever if you want. Dividing these. So, like I said, you really needed to understand multiplication before you can talk about dividing roots. Just like with multiplying, you can divide, or I should say reduce. If you want to reduce, you can reduce outside and outside together, and then separately inside and inside together. If you have a single thing, you're not adding or subtracting on the top and bottom. So, for example, if I wanted to simplify, say, 10 cube root of 24 x to the 4th over 2 cube root of 3x, what I could do here is I could look at the outside part. 10 divided by 2 is 5. And then I could look at this inside part. 3 goes into 24 8 times, and x goes into x to the 4th, leaving you x cubed. And then I could break that down. 5 cube root of 8 is 2. 3 divided by 3 is 1, so 2x. So 10x. So I could do that. Most of them aren't going to work out that nice. And especially we don't want to leave a root on the bottom. So we're going to do what we call rationalize the denominator. Rationalize the denominator. So, for example, the cube root of 2, that's an irrational number. So if you had that on the bottom of your fraction, it would be irrational on the bottom, and you'd want to make it a rational number, like 2 is a rational number. So we don't want roots on the bottom, and so we're going to have to fix that. So let's start with something a little bit simpler than something like this. Let's say I want to simplify 1 over the cube root of 4x. Okay, so I don't want this root on the bottom. It's okay to have roots on the top, just no roots on the bottom. And so I'm going to ask myself, well, why is this root not breaking down? Why can't I do this cube root of 4 and get a nice number with that? And the problem is 4 is not a perfect cube. 8 is, or 27 is, or 64 is. So what I want to do is I want to ask myself, what perfect cube is closest related to 4? And to understand that, you have to realize 4 is 2 squared. So the most closely related cube to that would be 2 cubed, or 8. So I'm going to multiply this on the bottom by a 2 under the cube root to make that an 8, because then that will break down evenly. Same thing with this x. There's only one x, but in order to take the cube root of it, I need 3. So I need 2 more x's. So I need one more 2, because I already have 2 in the 4. And then I need one more x. But I can't just multiply the bottom of an expression. I have to multiply the top by the same thing. So understand what I'm doing here is I'm asking myself, what is the bottom missing to make it a perfect cube? And the 4 is missing another 2 to make it an 8. And the x is missing 2 more x's. So you're asking yourself, what is it missing on the bottom? And that's what you're going to multiply top and bottom by. So 1 times that is just that. This is going to be the cube root of 8 x to the 3rd. And then that bottom is going to break down. So cube root of 8 is 2. Again, 3 divided by 3 is 1, so 2x. That is the answer. That's how you rationalize or simplify the problem. We call it dividing. It may not feel like you're really dividing a whole lot, but you're fixing the bottom so that it doesn't have a root in there. So what am I missing on the bottom? That's what you need to be asking yourself. So simplify 3 over 2 square root of 5x. So what am I missing on the bottom to make that a perfect square? So the 2 is fine. Don't look at the 2. 2 is out of the root, but it's the stuff in the root. So I got a 5. I need that to be a 25. So I need another 5. 5 times 5 is 25, and I need another x. And whatever I do at the bottom, I got to do the top. So 3 square root of 5x over 2 square root of 5 times 5, 25, x times x, x squared. And again, that's going to break down into 5x. So 3 square root of 5x over 2 times 5x is 10x. So when you have just one term on top, one term on the bottom, and you don't want a root at the on the bottom at the end, rationalize the denominator. Okay. So what am I missing on the bottom? That's what you need to ask yourself. So now, what if I have a 2-term denominator? Okay. So let's say I have something like 3 over 2 plus the square root of 5. And again, I don't like roots on the bottom. I can have roots on top, but not roots on the bottom. How do I fix that? Well, I can't just multiply top and bottom by root 5. That would be the kind of the instinctual way, is because that's how we did it before. But if I did that, so come on, let me get up there. All right. If I attempted that, I'll just multiply top and bottom by root 5, just like I did before, right? Well, the problem with that is, while that will give you the square root of 25, which will break down, you have to multiply all of the bottom, and so you get 2 root 5, and so on the bottom, you still got a root here. You didn't get rid of it. So to get rid of that root on the bottom, we're going to have to approach this indirectly. So don't do that. Hope you didn't write it down. That's, like I said, it's a natural kind of, we just talked about that's how you do it, right? But when there's 2 terms, it's more complicated. And what we're going to do is we're going to use and let me just say, you're only going to be facing in these kind of problems, you're only going to be facing square roots. You're not going to be facing cube roots or fourth roots, whatever, because the trick here, especially for this one, is to make this a perfect square. And we're going to use this relationship. We're going to use the relationship that a plus b times a minus b equals a squared minus b squared. The difference of squares. That's how we're going to do this. And these two things, I mentioned this before, but I don't know how many people caught it. These things are not opposites. Notice the A's have the same sign. It's the B's that are different. So they're not opposites. To be opposites, both signs would have to be different. These are what we call conjugates. Only the middle sign has changed. So what we have here is we have half of the difference of squares on the bottom, and we're going to multiply by the other half. So in this case, 2 minus the square root of 5. So that's what I mean by it's indirect. We're not going to try to get rid of the root part. We're going to try to make the bottom the difference of squares. So 6 minus 3 root 5, and then you can FOIL this out if you want, and I'll just go ahead and do that. 4 minus 2 root 5 plus 2 root 5 minus the square root of 25, but what you'll see is these two will always cancel out, which is what we want to happen. That's the difference of squares part, is both ends squared. And that's a minus 5. So 4 minus 5 is negative 1. So negative 6 plus 3 root 5. Now this one, the bottom came out to be, 1 or negative 1. A lot of times you'll have a number there, and you'll look to reduce those fractions if you can, looking for common factors. But maybe I'll do another one, just kind of, hopefully we can run into something like that. But let's say we have, okay. Hello. Why aren't you writing? Excuse me. My writing tool died on me. Okay. Great. Oh. Working. Okay, it's working again. All right. Technology. All right, so let's say I want to simplify 2 plus the square root of 3 over 7 minus the square root of 3. So again, I don't care what's going on top. What I care about is the bottom, and I want to set up the difference of squares. So I have half of it. What's the other half? 7 plus the square root of 3. And whatever you do on the top, or on the bottom, you got to do on the top. So again, I'm going to FOIL those out. 2 times 2 is 14. 2 times 7 is 14. 2 times root 3 is 2 root 3. Root 3 times 7 is 7 root 3. And then 3 times 3 square root of 9. And then on the bottom, again, you can FOIL this out, but you're going to end up with this, right? Because you're going to get positive 7 root 3, and then a negative 7 root 3, and then negative square root of 9, and these two are going to cancel each other out. Square root of 9 is 3. Square root of 9 is 3. So combining non-root parts, 14 and 3 make 17. 2 root 3 and 7 root 3 gives you 9 root 3 over 49 minus 3 is 46. Now, when I go to reduce, what I'm looking for is there a common factor between 17, 9, and 46? Notice all of these are outside the root. And you could, if you say they were all divisible by 3, for example, I could divide all 3 of those by 3, and that's how I could reduce it. An alternative way is you can get, a 2-for-1 deal, right? You can split this up into 2 fractions with a common denominator. and then see if, 17 and 46 have something in common. And then again, 9 on the outside and 46 on the outside have anything in common. They don't. This is 2 and 23. Both of those are prime. 17's prime, and 9 is 3 and 3. There's no 2 with 23 in that. So it doesn't reduce. And so I would probably leave it this way. There isn't much reason to separate it. But if you did see a reducing thing, you might separate it to do that reduction. So the conjugate is what you're going to multiply top and bottom by when you have 2 terms on the bottom. You have 1 term on the bottom. What you're going to be asking yourself is, what is inside the root? What is it missing to make it a perfect root? And that's what you're going to multiply top and bottom by. So 2 terms, more complicated. 1 term, what is it missing? Okay, so I'm done. We got about 10 minutes if you want to work on that. Do you have questions or whatever? But that's it.